Hi everyone. Vector Podcast is back with season 3, and I'm super excited to be talking to my guest today. And there is a connection with this episode between this episode and the episode that we recorded with Yuri Malkov about one of the most famous and popular vector search algorithm, HNSW. And I'm talking today with Leo Boytsov, who is the senior research scientist at AWS, and he is also a co-author of NMSLIB. And NMSLIB is today used at OpenSearch and probably some other places that I actually don't know, and I hope to learn it as well today. This is just exciting, and I think you know, goes without saying that the whole field stands on the work done by people like Leo and Yuri and others who actually developed the core algorithms and popularize them, improve them over time, and then the story unfolds from there. Hi, Leo, how are you doing?
Hi, thank you for introducing me, Dmitry. It's a great pleasure to be on the podcast.
Yeah, it's my pleasure as well to have you. Traditionally, we start with the background. Uh, can you say in a few words your background, maybe how you got here, and what's your story in search, vector search, and maybe LLMs?
Yeah, sure. Yeah, so my background is pretty long. As you, um, I've had a rather long career, honestly. Well, in my current capacity, as you mentioned, I am a scientist at AWS AI Labs. For 1 year, I was working on code generation, but early this year, I moved to a Q-Console team. Q-Console team works on question answering chatbot that answers questions about various AWS services. So you can ask, like, I don't know, it's like, where's my EC2 instance? Things like that, and how I set up things. But I have to make a disclaimer that today I do not speak on behalf of AWS, and I cannot talk in details about my work there. So as I said, I had a really relatively long career. Um, yeah, so nearly all of my life, I have been a computer science geek with a passion for building cool stuff and solving hard problems. Yet my professional career started in rather mundane fashion. So I started working on client and server software for financial systems. This was not my favorite subject, but pretty much the only one that was paid reasonably well at the time. So I had to do a lot of front end and back end engineering using various SQL databases. I was not satisfied with my career, but luckily I got really interested in algorithms, in particular retrieval algorithms. So I started working on this topic of retrieval algorithms, first part-time, then full-time, but largely as a software engineer, less as a researcher. And as a software engineer, I worked for various companies, including two tiny startups and the Russian search engine and Yandex. So later I moved to the United States and worked on the search engine PubMed at the National Center of Biotechnology Information. First, again, that was a common topic in my career. I was doing a lot of front-end development, but about like last 4 3 years, I worked primarily on retrieval of the core engine. In particular, I invented a pretty neat trick to speed up weighted Boolean retrieval. And around the time, I also realized that it would be hard to get a research position without a good degree. So that motivated me to apply a bunch of universities, and eventually I got accepted by Carnegie Mellon, which was a huge lock. But yeah, so I did my PhD studies there, and during these studies, I worked on a mix of machine learning and algorithms without any deep learning. So the vector search, or rather similarity search, was a part of my graduate studies. So yeah, I didn't use any deep learning though. It was a mix of classical machine learning, word-to-vec style neural networks, and retrieval. So what is like an interesting part of that story is that my advisor, Eric Nyberg, he worked on question answering. And together with his students participated in development of IBM Watson. That's an amazing trivia playing system that like in 2011 defeated human champions. So that was like one reason why I chose my advisor. It was like such a cool topic to choose. But pretty quickly I learned about the system and realized, oh, like it's actually really just not just, but it's largely a search engine on steroids. So retrieval, IBM Watson, I have a blog post about that if anybody is interested. But then retrieval, it's basically really retrieval-based extractive question answering systems. So if you want to improve question answering, you need to improve retrieval. So that's how I got back to working on core retrieval algorithms. And again, I saw an opportunity, and my big research question was, how can we do information retrieval using more advanced techniques rather than lexical search with BM25? Because before BERT, nowadays, like everybody just uses like BERT-based models or um, any like other transformer-based models to create dense vector embeddings, and they are quite effective. That was not the case when like 10 years ago. So whatever we had there was pretty ineffective for retrieval. And so my thought was that because the single representation was not effective for retrieval, those need to be somehow combined, assembled. So you basically don't get a single representation. You use a combination, you use combined similarity, and then you treat this similarity as a black box, and then you apply a generic retrieval algorithm. So this was a pretty like in hindsight, that was a pretty ambitious project that required working on both design of effective similarities and retrieval algorithms. And that's why well, one, that's where that NMSLIB library turned out to be very useful. It was instrumental to this work, although it was created for somewhat unrelated reasons. Okay, so that was an overall rather bumpy ride. Things didn't work well initially, and I got a lot of help from other people, in particular from my co-author, David Novak, who proposed an amazing improvement for one of the algorithms in NMSLIB. Yeah, and so we published, and that opened path to my graduation. And when I was writing my thesis, and yeah, I was found like a bunch of issues with my previous approaches and realized that I could also use like a HNSW like algorithms, which were not like core part of my thesis work. And I got even stronger results, but that was like a little bit too late to publish and use otherwise. Moreover, that the similarity that I use was a sort of a face palm realization that the similarity that I used, like we treated it completely as a black box, and it worked. It was effective. It was more effective than BM25 on the collections that I used. But I didn't realize that this black box similarity was actually representable by another product between two large sparse vectors. My another former co-author, Chris Dyer, pointed this out. And if I embraced this sparse vector approach from the get-go, it would have been a much easier problem to solve from both engineering and scientific points of view, even without BERT. And okay, it could have produced some more impact, but yeah, a little bit too late to dwell on this now. Okay, and enough with that. I graduated 6 years ago, and since then I have been working as a researcher, scientist, and engineer on deep learning. More specifically, I have been training models for speech recognition, computer vision, and retrieval. Despite this diversity, things have come a full circle, and I work on question answering systems once again. Yeah, that was pretty much about
Yeah, amazing story. And
my
like
background.
it's thank you for that. And it's like the story tends to repeat itself, but at the same time, if we find the topic still exciting, and it seems like you are still very interested in question answering and improving building blocks of that, it's kind of cool, right? So that we are able to come back to some of the topics, pick them up on a different level. That's amazing. And yeah, there is a lot to unpack. I almost wanted to ask your the moment you spoke about sparse and dense. I wanted to pick your brain on what's your take on the model called SPLADE and SPLADE V2. I don't know if you're familiar with that model, but basically, you know, there is always this discussion: should we take lexical search, combine it with dense search, and then do some kind of hybrid formula on top? And then how do we even learn the parameters of that model, right? Depending on the domain. But then there is a drastic sort of approach. Let's not do that. Let's just take a complete model which can handle both. And then you can also support what dense search doesn't support, like exact phrase searches. What's your take? What's your general intuition about that? How do you think about this?
Oh, that's a super interesting question. I have one like clarifying question though. So before I answer, I you said that some people want to have like a single model that's doing both. Could you elaborate a little bit on this?
Well, I guess maybe it's not that they want it, but it's like the development when uh, instead of sort of, combining these disparate sources of results, one coming from lexical search, which is kind of like well-known BM25 driven, I guess, and then the other one is more uh, like more modern in a way that everyone wants to get exposed to, then search, and then you need to somehow figure out how you combine the results, right? So one is designed maybe for precision lexical, the other one is designed more for recall, right? Because the vectors are not they don't have as many dimensions as the sparse vectors. But then you still need to figure out, okay, how do I combine these two? And usually people cite reciprocal rank fusion in what I hear, but there are other methods as well, like even clustering based. Um, but then that's one approach. Another approach is just stop doing that, I guess, if I fully understand what SPLADE does, and then you encode with SPLADE your data once, and you retrieve, you use its capabilities to also retrieve exact prices, right? So effectively, ideally, you don't need the lexical matching engine anymore. But maybe I'm completely wrong. I wanted to hear your opinion on that.
Okay, well, it's again, it's using your words. It's a lot to unpack here. The I'm still not quite sure what you mean by having like a single model. Although maybe let me try to maybe start answering questions, and you can like interrupt me and guide me into the the other direction if needed. So first of all, we have what's interesting about natural language is that, and it's very different from computer vision domain, is that we usually represent we have multiple ways to represent text. So in computer vision, like usually it's just like each images are traditionally represented as vectors. That was the common theme. But in natural language processing, we started with the so-called bag of words representations, where a document was represented by basically sparse vector, where you will have either zeros and ones, which means the specific term is present or not, or maybe weights, not just zeros and ones, but weights. Uh, but then with development of deep learning, and then actually it started a little bit earlier with people learned how to represent uh, text using fixed size vectors, and that was like using principal component analysis. And this is not a very natural representation for text, and it didn't work really well initially. But now we are having good results. So we have like two representations, and there are different approaches to combine those, of course. One is this just if you want to do retrieval, you can indeed just do the lexical based search. You can do k-nearest neighbor search and vector representations, and then you can somehow merge the results. You can use ranker. But you don't have to, and that's the so-called hybrid search. But the hybrid search can exist in different versions. So if you want to combine it sort of in a single model, why don't you represent each document using both sparse and dense vector? And when you're computing the similarity, you can compute the similarity between sparse parts, between dense parts, and then combine them somehow. For example, using a weight. And that's in fact what I was trying to do in my thesis as well, because I was doing, my similarities was basically an ensemble of several similarity scores for at least two representations. And that could work. There's, of course, modern instantiations of this, and there's a paper, I think, authored by some Google people, where they did exactly like this. They combined SPLADE and some dense vector embeddings. And that can work apparently a little bit better than, or sometimes maybe a lot better than basic representations, like each representation specifically. So with both approaches, of course, there are issues that you mentioned. So I don't know what's the best approach there, and I don't have a crystal ball regarding what's the best path forward. But with dense representations, clearly the problem is that you have to pack everything into the fixed size vector. And as your document is getting bigger, you basically, the vector size, the amount of information you could store is the same, but your document increases in size. So you would possibly expect some deterioration in quality. But another reason why you can see deteriorating results just because some, like you have fixed representations, the number of words is huge. And like in a regular person knows like about around like educated person knows about 30,000 words, but in reality, like internet has millions of words, right? And the words are not just only words. There are things like product identifiers, right? If you wanna, and sometimes people will do product search, they will search something they want to buy, and they would, copy paste those or type them in, and then they got squished uh, in that dense vector, so it cannot be precise. There is an interesting paper authored by Niels Reimers, sentence board author, where he has like some experimental and even theoretical evidence that as the collection size increases, so the dense vector search can deteriorate just because there would be some false positives and meshes due to, like squishing a lot of information together in a fixed size vector. So, I mean, it's quite possible, but I haven't seen like a full off for this work, so I don't know if like how much of a problem it is in practice. And coming back to the sparse representations, so yeah, they could potentially resolve this issue, but not necessarily with the SPLADE-like models. Well, the problem with SPLADE is that SPLADE models, they create those sparse representations using not the words themselves. They're using subword tokens. So as a reminder, with like models, like with transformer models, um, they create this sort of new sort of vocabulary that has some complete words, but most words are incomplete. So like they have like extract prefixes, suffixes, parts of the words, and this is your new vocabulary. And the difference between this new vocabulary and the actual vocabulary that people use or use on the internet is that it's limited too. It can have like 50,000 tokens, maybe 200 tokens in some of the advanced multilingual models. But we really have like millions and millions of words. So of course, that would also lead to some deterioration in quality, false positives, and especially if you try to represent represent long documents using this fixed size fixed size vector. So it's sort of sparse in it's more sparse in some ways, but it's still fixed size vector. Does it make sense?
Yeah, it does. And I mean, it's very insightful what you said that, like basically to make my question much more succinct, I could ask you, could we just use SPLADE for everything? And like instead of, combining different approaches, just use SPLADE. But you basically answered it really eloquently. You said that SPLADE itself has limitations, right? For example, that would not allow us to properly embed all variety of the language, and then obviously dealing with longer documents is another issue.
There is an interesting extension to the to this. So I was just recently listening to a presentation on the extendable SPLADE, where they extend the vocabulary of SPLADE by adding entities. That's one interesting direction of work. But another interesting direction is like the so-called like DeepImpact models, where they take a document and they do document expansion using like the doc to query style models,
Yeah.
and then they for each token, I think in the document they are learning a weight, and so this is like a little bit more less limited, I think. But in the end, I think it's whenever we yeah. So basically, if like to be able to handle those like rare, we need lexical representation to handle, you know, bigger vocabularies, and it's probably hard to model with just fixed size vectors.
Yeah, it makes a lot of sense. At the same time, we also know that, well, it depends on how you model this, but lexical approach, like vanilla lexical approach, would miss semantic links, right? And sort of understanding of larger context, because all it does is that it kind of looks through the BM25 model at the words, and sometimes it just pays attention to some words, but doesn't pay attention to other words, and it may miss the main point of the query, right? But of course, this model still worked for, and you worked at Yandex, you know it best. These models worked previously probably by virtue of training the users that, hey, don't give me the full sentence, just give me like, specific words, like chopped list of words that I need to look up. And that's how, I guess, inverted index worked out. And of course, you need to have, on top of that, you need to have very smart re-ranking strategy to pull up the documents that are really relevant, right? But I guess today we have this new, well, I keep calling it new, but it's not maybe necessarily that new, but it's still fairly fresh development of dense retrieval that not many companies I think have onboarded in their products yet. But it's a very interesting direction, and still you need to combine the two worlds, right? So it sounds like from what you said, the only way to get better quality is to combine these approaches rather than try to develop one single holistic model to handle everything.
Oh, yeah, it's a great question. I actually don't know what's the best path forward is. So I highlighted the deficiencies and advantages of different approaches. Um, but I also want to comment on the deep impact model. The deep impact model, I think the way maybe I described it, uh, it sounded like it is like a BM25 model, but it's actually not. So maybe we should have like we're talking about sparse representations, like learn sparse representations, because it's a bigger topic and it's much bigger topic than most people realize sometimes. So people know BM25, people know dense vectors, and these simple things, but there is a lot in between. So first of all, what you can do, and that's what people did, and even the doc to query is the most famous way to do so, but it was actually not even a single group of people who proposed this. So what can you do? You can take a model, a deep learning model, contextualized model, maybe not necessarily contextualized, but contextualized models, they do better job because they look at the model as a whole, or the document as a whole. They don't like look like at individual chunks of document, right? So they kind of can understand what the total meaning of the document. And then they propose new uh, keywords or new terms. So some like synonyms that could have been in this document, but they are not. And if you add these documents to the if you add, sorry, pardon me, if you add these terms to the document, then these missing synonyms are there. You can index this document. So basically, this is document expansion. And you can do document expansion, and that helps resolve that lexical mismatch, mitigate lexical mismatch between query and documents. And I claim it's easier to do this expansion. There are, like, of course, approaches that do query expansion, basically adding synonyms at the query stage. But my claim is that it's much harder to do this accurately because there is much less context. So this is one, um, this is one direction of like fixing things and creating sparse representations. Like there is a SPLADE model. What does a SPLADE model do? It's completely sort of it's doing something completely different. It looks at the document, and there is a vocabulary um, like bird tokens, and for each token it gives you a weight. It looks at the document, sort of understands its meaning, and says, "Oh, this is a word or a prefix of a word. It should have this weight," and that's how you get a sparse representation. But with DeepImpact, you're doing something slightly different. So you take a document and you do this document expansion. So you add words like synonyms, but then you don't index this document using BIM25. Why? Because BIM25 is clearly old style and it doesn't take like context into account. So instead of that, you train a transformer model that would give you weight for each term in a document, in the expanded document. And then you use this for retrieval.
Oh, that's very
So that,
interesting. And that's
yeah,
called deep impact model, right?
yes.
Yeah. We should link that. I guess there is a paper for that as well, and we should be able to link that. Yeah. That's very interesting. And it's also interesting that what you mentioned about the dense model sort of not able to capture everything that you want them to capture, and yet this becomes a building block in the application phase, like for example in RAG, retrieval augmented generation, because effectively the only method that I heard so far of, which is circulating a lot, is just chunk it up. You chunk all documents up, and then you hope that the chunk size is less or about the same as capacity of the model, right? Because otherwise it will chop off the end and you will lose the part of the meaning. Or you also apply some methods like some level of overlap, right? So you can then index few more chunks in the same entity and then try to query. And then, interestingly, you can generate questions out of chunks that these chunks might be able to answer, and then you search those questions instead of the chunks themselves, right? So which comes back to what you said about doc to query, I guess. So it's very interesting that
Yeah.
like these, like we are sort of like standing on a set of building blocks that themselves should be optimized and optimized and optimized, but I guess we're already in the phase globally when everyone is trying to derive value from LLMs and RAGs and everything, right? And yet we can stumble upon some really tricky situations, like you
Looks
explained.
like we have a lot. Yeah, looks like we have still a lot of research topics
Yeah,
and a lot of unanswered questions.
yeah. I wanted to a little bit digress from here to the work you've done at NMSLIB, and I want to read it from the GitHub repository. It's a non-metric space library, um, and I did spend some time in my pre pre-work life, when I was studying mathematics, and we did study a bunch of metric spaces. I have never realized I would never like imagine that this highly theoretical stuff would now connect so deeply to practice, and it's amazing. But can you tell me why it's non-metric space library? Isn't it so that the whole idea of vector search is that we choose some metric, cosine or dot product or whatever it is, and that's how we express the semantic similarity.
Great question. So the reason why it is we decided to not limit ourselves to metric search because we felt, and that's also a feeling of other people, is that metric search is limiting. So it's not expressive enough. It turned out to be true to some degree, but not as much as we hoped. And indeed, in many cases, and while we were doing so, the representation learning was not as developed as it is now. So we felt like we need to be able to people will engineer those complex similarities and would need to support retrieval using this complex similarity. This did not happen. But what I think happened, and that's I want to connect this to my statement that in the end of my graduate studies, or rather after defending a thesis, somebody pointed out that the similarities that we were using were basically representable as the sparse unit product between two huge vectors. So it's some sort of, it becomes similar to either DeepImpact or SPLADE. And in fact, so the similarity is the maximum unit product. It's not the cosine similarity. And the search, like the search procedure is called maximum inner product search. So you wanna retrieve documents that have the maximum inner product between query in a document. And the and this is a symmetric similarity measure, in some sense symmetric, but it is not a metric, and it's not easily reducible to the say to the cosine similarity and to the searching using cosine similarity is actually fully equivalent to searching using the Euclidean distance. For the inner product, you can reduce this search to cosine similarity and Euclidean distance, but turns out that this reduction affects efficiency. And it's somewhat like bigger topic for a discussion. But what happened is that people say at Lucene, who are maintaining Lucene, they were adding support for the maximum order product. And Vespa did this, and they did this through this trick to reducing of maximum order product to cosine similarity NL2. And I argued that there is research showing that this is suboptimal, and there was a discussion, and as a result, they basically didn't do this. So long story short, I think a lot of things are so non-metric similarity search as in general turn out to be not so useful, but there are some instances like maximum inner product search where we do have things that are non-metric and it is widely used.
Yeah, that's amazing. That I think I hope that
I hope this
equally,
makes sense.
yeah, it does, and equally as I'm learning, I hope my our listeners are also learning on this, because oftentimes when you plunge into a new field, let's say dense search, all you see is what is being popularized, and you may go down the rabbit hole. So I'm really excited and thankful that you are able to share a much wider perspective over things. And then also, most interestingly, your work and you say you're a co-author of NMSLIB besides other authors. Your collective work is also now used at like for open search, right? Engine, which I believe I also had a chance to test at some point, and like it's a C++ library that is then somehow loaded uh, of JVM, and basically then search is performed using HNSW. Can you tell me a bit about that, like that story of how did you end up, connecting these two, NMSLIB and HNSW? And here I will probably link to the episode with Yuri that is quite popular today.
Yeah, well, first of all, I have to say that, I mean, most popularity, like close to 100% of animal sleep, is certainly due to the development of HNSW, which was Yuri's creation, not mine, and we affected it only very minor ways, because I mean, we provided the platform, and yeah, so I think one trick that Yuri borrowed, which I borrowed from Kgraph, was the efficient algorithm for membership checking, but that was it. So the animal sleep, but animal sleep on it was like creation of several people, and it was like has like a rather wild story. So it was never planned. It is sort of random how it developed. Um, so in 2012, I attended the conference where I met Bilik Naidan, who was working on, he was doing his PhD on similarity search, and and we found that like a lot of like we shared some interest in particularly in retrieval algorithms, and we decided to do some joint project together. And then my initial interest was how do I support non, it was somewhat academic topic, non-metric search is as I explained before, it's still like largely of more like academic interest because a lot of things are really metric or at most maximum winner product search with a sort of almost cosine similarity, almost symmetric. And yeah, so that was basically purely for academic interest, and I connected it to the machine learning because I saw an opportunity to use machine learning to support generic algorithms that would do k-nearest neighbor search with non-metric similarity, such as scale divergence. Yeah, so we did it as a machine learning course project, and we published a paper at NORIPS. And it could have stopped at this point, but then I also like that conference. I got like I met other Yuris that conference or just through internet. I met with some of with Yuri other co-author Alexander, and they both work at Merrill Labs company where they developed small world graph approach, and that was like a Java version. And so Alexander was really interested to prove that whatever algorithms that we have in MSLib, and we're tackling generic search in generic spaces for generic similarities, and he was eager to prove that the graph-based algorithm are actually truly generic. And this is why he and his student created the first version of a small world graph in NMSLIB, so basically contributed that version. And that was like really super slow. I sped it up at about 10x, and that was the version that we used to win the first ANN benchmarks. So it was pretty good, but it has issues. And one issue that um, was fixed thanks to Yuri sharing with me some early version with HNSW, and I looked at the code. It was not as like fast version that he created later, but it already there was fixing something. And maybe we didn't realize. He showed me that piece of code, and I realized, oh, like there is actually still an issue in SW graph. So both SW graph was improved, and Yuri like contributed HNSW to NMSLIB. So it greatly it was like a huge contribution, like big step forward. It won the second NN benchmark competition. The improved SW graph was, I think, the second algorithm. I have a screenshot of this somewhere, which I sometimes include into my job talks. And the HNSW also influenced FAISS because they realized, oh, like they actually knew about K-graph and knew about the graph-based retrieval, but there was one important reason why they didn't use it. You can ask me why. But anyway, so it influenced FAISS and a lot of other people. And of course, yeah, that Yuri created like a huge, that was Yuri's work had like a huge impact, and yeah, the rest is history. But I think Yuri shouldn't complain. No, he has great career at first. He has great career first at Twitter, and now is at OpenAI. So yeah, good for
Yeah,
him.
it's amazing story. Just to close off the loop, why did FAISS did not implement the the approach you had?
This is really interesting thing because that's one of my favorite pieces in this story. Well, turns out that the graph-based retrieval algorithms, they had a long history. So a lot of this was rediscovered, and the pruning heuristics and like the basic algorithm, they go back to papers in the 80s and 90s. But people did not use it. In one hurdle was the inability to efficiently create those k-nearest neighbor graphs. And k-nearest neighbor graph, it's a simple concept. You have a data point, and you need to find some data points that are nearest neighbor of these data points, and then you connect to them, modulo some post modification of this graph. But how, like, if you have n points, it is in the brute force search approach and squared computation. How can you do this efficiently? How can you approximate this? So the way how it was done before, people were coming up with fancy algorithms how to approximate this operation. And those fancy algorithms were not particularly scalable. And K-graph, I think, is not particularly scalable. We played with it. We actually incorporated K-graph implementation into NMSLIB. And it was indeed hard to create larger graphs because it's an iterative algorithm, and yeah, it's not very scalable. But what Yuri and co-author did for as small world graph, and it was before HNSW while they were at Mera Labs company, they realized that they can combine retrieval and creation of the graph, and they can do it efficiently, like in what, like using modern terminology, embarrassingly parallel fashion. And that was, I think, one key missing block that prevented graph-based algorithms to become practical. I
Yeah,
hope that
that's
makes sense.
yeah, it does. It's very like what excites me in this story that you shared is that how serendipitous this like the discovery process is, right? And like
Yeah.
something that feels like random leads to, I don't know, creation of the industry, right? You could largely say that the new industry of, vector databases and vector search and now RAG on top of that is created because you guys worked on practical implementations of something that was also uh, that stood on the shoulders of some of the inventions and research done before that, and so it's kind of like natural progression. But it's amazing how it's just on the verge of you not meeting someone at a conference could basically lead to possibly not creating an industry, right? Quite possibly.
Uh, uh, I, well, thank you for the kind words. I mean, of course, it's not because of us. If not for us, I think other people would have done this. I, yeah. So I, the, but anyways, so I think we did useful work, and clearly people are using HNSW a lot, and people using NMSLIB, even though it has like a lot of issues, but it's was still ended up being used rather widely. And the one reason why it was used so widely because people needed a library, a Python, basically a library that would do k-near snare research, and it would do it from Python. And people often take these little things for granted, but say initially, NMSLIB didn't have Python bindings. And to participate in benchmarks and have something useful, you would need to have Python bindings. These Python bindings were written by Bilek. I didn't create those bindings, so he created those bindings, the first version. So there you go. That library was possible to use, and there were at the moment the it was not such a big choice of libraries to do Canyon search. So in terms of the competition, there was Annoy, which was slower, noticeably slower. There was another library, Flan, which used similar algorithms to Annoy, but it was less optimized. And it was also slower for retrieval. There was like K-graph, but it was not like so easily usable. And yeah, basically that was it. And later came FAISS, but it was only released, I think, a couple of years later after, well, definitely after. Yeah, it took several years for FAISS to appear and people started using it. So at some point there was vacuum, and anonymously filled it. Now, like other approaches are taking over. Yeah. So yeah, in summary, there was indeed a lot of serendipity, but I wouldn't take credit for creating an industry. It would have been created without us for sure. Yeah.
Yeah, maybe or maybe not. And it's also, well, I think it's quite for the lack of a better word, typical of the inventor not to uh, recognize the impact they're making, because the moment they do recognize that, that's probably end of story. So like you need to be constantly sort of low ego and pointing at the goal. And I think this is what you're doing, and that it feels like this is your approach, but you also do quite a bit of impact. Um, I I could ask a ton of questions, obviously, and I could relate also to the fact that what you explained about some of the struggles, like how to optimize these algorithms, because at some point I did embark on participating in billion scale ANN benchmarks, and I think I failed miserably, but at the same time I did have some code which worked on a smaller scale, and one of the building blocks there was HNSW with very simple, I would say with very, very simple intuition that you just make I think several passes through the data set, and you try to find points in space that are closer to each other. And then you would push them to some common bucket. I called them shards, and then you would build an HNSW index for those shards. The only thing that I couldn't figure out is for those shards, I still needed to have an entry point to quickly sort of identify which shards I should go down, uh, uh, through when I uh, compute, like when I find similar documents for the query, and I did attempt to modify HNSW code in the NMSLIB, to like get me only first layer of the graph so that I can pretend that's my layer for entering the shards. Uh, I just ran out of time, but I think it was very exciting, and also thanks to the organizers, we had access to really beefy machines, which I think I haven't been giving like good use. I was mostly burning the, CPU capacity and memory, but I think it's an exciting field. And what I hope is that, like the vacuum that you mentioned, that it doesn't happen, that this torch will be carried forward, and then someone will get excited about and not afraid of trying new things in this space. Are you yourself still like looking at obviously you're looking after NMSLIB, but is there something that particularly excites you in this field that you would be working on or you are working on?
Yeah, great question. So first of all, yeah, I'm not sure if I would do any work on vector search in the I have been actually not maintaining enough sleep pretty well recently. I'm just didn't have a lot of time, and there was an issue with building the. So I will still fix and support later version of Python for sure. But it was like like piecemeal work. I found like say half a day to fix like Windows build and something else popped up. Yeah, so it is an exciting field, but it's also become really busy. And another thing is that I still see the main focus. It's not a very appreciated field. So the like you said, I mean, there's a like really nice words that like that helped industry to be created. And maybe it's true to some degree, it is true. But yeah, is it appreciated by your potential employer? No, it's like zero appreciation. So it is a niche. Um, it was and still is somewhat niche topic, and most people, of course, are interested in how do you solve intelligence in that broad sense of the word. How do you create models that can reason? And if the model, like how you can combine them, that this is like this new agentic uh, ecosystem, and yeah. So all that stuff that really excites people, it is in this plane of or space of large language models, machine learning, deep learning, intelligence, you name it. Yeah, so that's why I do have ideas. I did tested some of them, but you know, things usually don't work. But I don't have time to think systematically about these issues.
Yeah, but I guess at the same time, you did create the base for you know for other people to innovate, and I think it's highly appreciated, really. Uh, I I
Thank you.
I also wanted to pick up the topic that originally sort of interested me when you popped up on my LinkedIn feed. Uh, you you made a statement about relational databases trying to implement search feature or sort of capability and sort of like miserably failing at that. Maybe you didn't use the word miserably. It's my word here, but I wanted you to a little bit like expand on this. Like, why do you think they tried to do that? And also, while they were trying that, what went wrong?
Yeah, great question. Well, first of all, I definitely wouldn't say the word miserable because the it has been success to some degree, definitely, and it's not over until it's over. So the people are working on this. So what I have been observing for many, many years, and as I said, I did start my career as a person working on databases and doing writing a lot of SQL. Uh, so, but the typical database is a very different beast from what you typically need to do information retrieval. So the first of all, the all like the early databases, or they are oriented, they achieve some trade-off between uh, so they need have good throughput in both inserts and updates, and they need to be able to update information pretty quickly, and also retrieval should be pretty reasonable. And they also support really like the data discrete like the data can be pretty complicated. That what they call that SQL schema, there can be multiple tables, and all of that needs to be supported. And so, of course, there are trade-offs to be made to make it possible. And again, to support generality, support efficient updates, support efficient inserts. But at the same time, if you're doing retrieval system, a lot of this is not necessary. So say for you want to do like keyword-based retrieval, you only need to, well, at high level, it's somewhat a simplification, but you need to memorize in which documents uh, you have which keywords, and then you have the so-called inverted index, where for each keyword you have a list of documents where these keywords appear, and it's much simpler structure. It permits much more efficient compression algorithms. Uh, so it's again, it's a different beast, and also in terms of efficiency of updates, once you compress data and once you represent it in a special way, it becomes much harder to make these incremental updates for which those early databases were applied. So that clearly there is a disconnect. It was somewhat removed with the introduction of the so-called columnar databases, but it's still like with columnar databases, I believe they actually do not favor those, point updates anymore. They are best to be used for bulk updates. And so basically, once you're doing bulk updates, yeah, you're sort of in this search engine area where yes, you change things in rather large increments, change indexes in rather large increments, and you don't worry too much about your information being like really up to date. You can wait maybe a day, maybe a few hours, but it doesn't have like an instantaneous update of the database. So there's different trade-offs. So yeah, of course there is a disconnect, and this is why it was always hard, I believe, to add like full text indexes to regular databases. But another issue with the disconnect is that, like, again, the retrieval often needs like really different set of specialized features. So if you have a relational database system, it's pretty hard to support this. For example, like tokenization, if you need to do tokenization in multiple languages. Yeah, so of course that spurred like the creation of those specialized tools with a lot of features like Lucene and Vespa, and databases are catching up, but there is still a gap, and it it's probably like going to be really tedious to support. Yeah, full set of features, and like you need to match Vespa. Yeah. So yeah, these are like my 5 cents of this
Yeah,
topic.
but I'm curious to sort of a little bit understand why do you think databases are still trying? Why are they trying to encompass this seemingly disparate ways of searching, right? When you actually, if basically, like you explained, if you need to have a fully blown search engine that can support multiple languages, tokenization, and so on, you better be using the likes of Lucene, Vespa, and maybe Elasticsearch on top of Lucene and so on. Why are they still trying?
I mean, they want customers. It's of course advantageous to be like one-stop shop. So they come to a specific provider and they have everything. So I listened to a podcast, the Rockset uh, co-founder, which was the Rockset, the one was acquired by OpenAI, but I think you recorded that podcast before they were acquired.
Yeah.
So good timing. And you can clearly hear that message, or like, we really want people to come and use our solution. So we have hybrid search, we have some support for ranking, we have this and we have that. Yeah, I can't argue against this being convenient. So definitely something something very useful for customers.
Yeah, yeah. Just a small correction. He's not a co-founder. I think he's VP of engineering, or used to be a VP of engineering in Rockset.
Oh, yeah.
But yeah, I mean, he brings the story, and I encourage listeners to listen to the episode. He brings the story of, RocksDB scalability issues from Facebook, and how it underpins, the further journey at Rockset. So uh, I feel like we could discuss for 5 hours, and I'm actually a big fan of Lex Friedman podcasts, where some of the episodes are really, really long, and you can listen to them for weeks. And I think I really hope that we can record with you sometime later, as well as as you have topics to share. But is there something, Leo, that you want to share? I don't know. It could be a paper you've read that particularly excites you, maybe a book or anything else that you want to say.
Yeah, I think yeah, great question. So I was interested a lot recently, and by recently I mean maybe the last couple of years, in how LLMs can be useful for search. In one particular interesting direction is like, how do you use LLMs to train smaller models for retrieval and ranking? And for me personally, it's a very exciting area of research. Yeah, as far as distillation is concerned, there were several interesting papers on the topic. There was, but basically a lot of that work revolves around creation synthetic data, synthetic queries based on the documents. Like you have a document that creates synthetic queries, and queries that you ask that query slash question, and the answer is in the document. So you have a positive or relevant document, and you can sample negatives from your collection and train a model. But there is also a line of research where they would try to create both queries and documents. So yeah, in summary, that whole not in summary, but that line of research was particularly interesting to me. Although there was some work before LLMs to create synthetic queries, it was not particularly well used technique. But one paper that stood out was the InParse paper from a couple of years ago, and we have reproduction of this paper. And that paper had um, a pretty quick follow-up from there were several authors from Google. They called it Promptigator, where they showed how this technique can be improved. And there was another follow-up with the same first author. Now she transitioned to DeepMind, and now they showed like now we do it like somewhat better, but they found one issue with the synthetic query generation approach, that not always the document that was used to create the query is the most relevant document. So you would think it sort of makes sense that if the question is being answered by this document, it is the most relevant document. But it turns out if you ask a question, there can be other documents that answer this question, and they can answer that question even better. And so they solve this problem using a relabeling approach. So they basically they do retrieval, they generate synthetic query from some document, they do retrieval, and they do then they look at the top, say, 10 documents, and they use another LLM to decide whether these documents are relevant to the query or not. Yeah, it's also a very interesting paper as well. And finally, the last couple of papers that I encountered were regarding creation of either creation of documents, either just jointly with queries or based on the queries. This is also a very interesting follow-up.
Yeah, that's amazing. Thanks for sharing, and I hope we can link all of these papers in the episode,
Yeah,
show notes,
absolutely.
because I think one of the goals of this podcast is to continue to be educational resource, not just entertainment. Maybe some people potentially view it as an entertainment in a good sense of word, when you want to sort of a little bit like break away from your daily routine and listen to some of the insights. And we heard a lot of insights today from you. Thanks a lot for sharing, Leo. And I wish you all the best in your projects and your current projects and your future projects. Um, and yeah, I mean, I would be equally excited to talk to you at some point as well, because it does feel like you have a lot more to say than I'm able to contain in a single episode.
Yeah, it's my pleasure. Thanks a lot for inviting me. I enjoyed the podcast. Enjoyed our conversation very much.
Thank you very much, Leo, and good luck. Bye bye.
Bye.